So this is G484 homework booklet question 8, and it starts off by asking about a collision between two objects which is inelastic, and we've got to tick the end of each statement that applies to an inelastic collision. So we need to work through these one at a time because we've got to decide for each one whether it's true or not. You can't just put 4 ticks down and expect to get the marks for extra ticks, as it were. They take marks off. So the magnitude of the impulse on each object is the same. Now that's not a law that you'll have learned per se, but think what impulse is. Impulse is force times the time interval, and we do know that the size of the forces on the two objects are going to be the same. That comes from Newton's third law, and of course that they must occur for the same amount of time. So it is true that the magnitude of the impulse on each object is the same. Second statement, the kinetic energy and the momentum for the objects are conserved. It's inelastic, so we know kinetic energy is lost, therefore it's not conserved. That's false. Total energy is conserved. Please tell me you tick that. After the collision, the objects have the same momentum. Slightly confusing because you could argue that afterwards the total momentum that they've got is the same, but in fact it was meaning that the individual objects have the same momentum as they had before, so no tick was wanted there. Yeah, I think that was a poorly worded question, that, but there you go, that's life. So I look at a diagram like this and straight away I'm thinking I've got to think carefully about signs, because I've got a tennis ball hitting a wall. It's coming in one direction, it's bouncing off in another direction. Before I do anything else, I'm going to, at least in my head, probably in actual reality, draw on here an arrow, and over the whole diagram, yeah, I'm going to draw on an arrow and I'm going to decide which direction is going to be positive, and I'm going to just mark on there positive. There you go, my beautiful handwriting. That direction's positive. So that's going to help me when I'm thinking about the signs as I go on. So a ball of 0.06 kilograms hits the wall at that speed. The ball's in contact with the wall for that long, it rebounds with that speed, giving a lot of information there, and which is quite makes for quite a good question, because you're going to have to pick out the relevant bits of information for each part of the question. So first of all, calculate the loss of kinetic energy. Straightforwardly then, I'm calculating the kinetic energy before, a half times 0.6 times 12 squared, and subtracting a half times 0.6 times 9 squared, and that, isn't it interesting, the arrow stays still and the writing goes with it. I'm going to have to get rid of that arrow. I'll have to just go in and draw in the arrow, won't I? There you go, there's my positive arrow. That'll now move with it, I assume, and that gives me 1.6 joules of energy. The magnitude of the average force exerted on the ball by the wall. I've got a time for collision, I've got velocities before and afterwards, I've got mass, I'm thinking Newton's second law. So I'm going straight in there with F equals delta P upon delta T. Now, because I've got my directions arrow, hopefully I can keep things nice and simple and straightforward. So remember, delta P is always final takeaway initial. Change in anything is always final takeaway initial. So I'm going to be looking at minus 9 times the 0.06 takeaway plus 12 times 0.06. Let's have a look at what that looks like. So there we go. There's the 0.06 times the minus 9 mv takeaway 0.06 times 12 plus 12. There's the mu, so there's the change in momentum, and the time I was given 0.15, so that gives me the rate of change in momentum, and rate of change in momentum is force, Newton's second law. So that gives me average force on the ball of minus 0.84. However, the question actually asked me for the magnitude, so that minus isn't strictly needed as part of the question. The magnitude of the average force on the wall by the ball, Newton's third law, 8.4 newtons. Simple. We'll take those marks when they make anything that give you anything that simple. They then straight away, and it's not obvious straight away why they're doing this, they jump in there and they ask us to state 3 assumptions of the kinetic model of ideal gases. Now, we've got the whole discussion between molecules and particles. I think what I'm always going to say is, say molecules, it always gets some marks. Particles sometimes does. So what do we got? We've got lots of molecules. I need lots of molecules, otherwise the averaging doesn't necessarily work. They're fast and they're moving with random velocities. That rapid thing is odd. I guess that they want that there so that we're in the position where a real gas will behave like an ideal gas. And of course there's a random distribution of them anyway, but they do like that word rapid there. Rapid and random velocities. We need the collisions both between the molecules themselves, so when molecules collide that needs to be elastic, and when molecules collide with the walls that needs to be elastic. In other words, we're not losing any kinetic energy. And then we've got our negligibles. We've got a negligible volume of molecules compared with the volume of the gas. We've got negligible forces between the molecules except in collisions. There's an interesting other way of putting that, which is to say that all of the internal energy is kinetic energy. Why is that the same? Because if there were forces between the molecules, we'd have potential energy. So by saying that we've got negligible forces, we're saying there's no potential energy. Therefore, we're saying that all of that internal energy is kinetic energy in an ideal gas. And then finally, the collision times are negligible compared with the times between those collisions. You only needed 3. We only needed 3. I've just given you all those 5 possibilities. So we've got to then use the kinetic theory of gas to explain how a gas exerts the pressure. I have to say I was slightly disappointed with the amount of rigour that was needed by the mark scheme here. Molecules collide with the walls. Okay, straightforward. Make collisions with the walls, make collisions with the surface. We then have 2 things going on. We've got a momentum change per collision, and we've got a number of collisions each second, and that overall, those 2 things together, give us a momentum change each second, and that of course is a force. Strictly all the mark scheme required here was that it exerts a force on the wall, but I think I can see them wanting where that force has come from, so I've stressed that there. Momentum change from each collision, multiply that up by the number of collisions each second, we get a total momentum change each second. And then the question isn't about force, the question is about pressure, so we just need to throw in there that the pressure is the force divided by the area. So that's G484 homework booklet question 8.